Alright, this is my random particle picker application. So the motivation behind this one was a little strange. I was playing video games with some buddies, and one of them kind of taunted me, saying I couldn't develop an application. He was using like a random wheel spinner to make decisions on this video game. I'm pretty sure he was using this one, where you just put in a bunch of options, like go left, then go right, and then you spin like that. So he said I couldn't build something like that. I felt compelled to prove him wrong and go a little bit overboard while I was at it. And that's how this app was born. So the way it works is it's a bunch of particles that represent the chances of being picked when chosen randomly. So right now the odds are pretty even for all four of these colors, but we could change this one to, like, I don't know, maybe half of its original value. Maybe we do this one for only 100. And let's do 100,000 on this one. And we'll keep that one the same. Now, if we want to pick a random option, all we have to do is select, and there's option 2, right? And so I've got these tracking lasers, and if I slow down the particles, you can see what it's really doing here. It's tracking that particular particle as it moves throughout the attractor. But yeah, the patterns that the particles are all following is they're following the Lorenz attractor here. And if you haven't learned about strange attractors, I highly recommend giving them some consideration. They're really cool. And there are other options here that we can configure. If we select a random particle right now, we're not really caring about it too much. Let's get inside the storm, so to say. But what we can do is we can lock onto that particle, and now the camera will track that particular particle as it flies around through the attractor. We can zoom out, we can zoom in, all sorts of fun stuff. Rotate around it, translate. It's not the most robust or crazy use case scenario. This was just kind of an experiment, an academic poke into Three.js, but I learned a lot. And trying to get all of these particles to work well together is not as easy as you might think. So what it is, it's a Next.js application, which is probably overkill. So version 1 of my particle system was it's simpler to understand. It's a lot more terse and readable. It's declarative. It uses dries points here from React 3 Dry. That's a library with a bunch of useful little helpers. But it's not always ideal, and there are some performance limitations when you start instantiating, a million React components, right? It's going to consume, it's going to block your CPU, and but it makes it really simple. Each particle here is kind of in charge of its own destiny. Of course, I've programmed it to follow a factor in this path, but the movement itself is actually being performed and computed within each individual particle. Okay, so this is the second version. Before we discuss all of this junk up here, let's just look at what the component itself is. So we've got these points. Now these points are different from the previous points that I showed you, the ones that can internally manage their own state and position and whatnot. These are rather raw points, dumb points, if you will. They don't internally calculate their next position. They receive orders from the outside. How do they receive those orders? Through this buffer geometry attribute called position. This is what we manipulate over time to change the position of each one of these points. And so you see our initial positions are randomly placed in a sphere. I've got a function further down that takes a bunch of points and places them in random spots inside of a sphere. That's to add a little bit of diversity into the starting conditions so that the attractor has actual visualization. If all of the points started in the exact same position and they all incremented by the same delta, then you just have one really bright point flying around. So first we gotta space everything out so the attractor actually gets fleshed out. But basically what we have here in our animation frame we just iterate over that attribute, right? We extract the positions there as kind of their own array, and then we iterate over the length of the array, and we change each, x, y, and z component of a vertex. We step through that attractor function, and we increment them by whatever little value it could be. It could be negative, could be positive, could be big, small, doesn't matter. We just increment it based on the delta. Actually, no, I take that back. We're not using the delta, are we, here? We're using the delta as a guard. So this is one thing that I learned early on, and I got help from the community because I was trying to figure out if I was running my strange attractor animation, if I was running that in a web browser and I would navigate off screen to a different web browser tab, for example, if I wanted to go check the news while this web page is running and animating all of these points, I went over there, checked the news, come back 5 seconds later, 10 seconds later, 15 seconds later, whatever. All of my particles will have flown off into the vast emptiness of space. And I just couldn't for the life of me figure out why the heck that was happening until someone finally pointed out that I was using this delta value to increment the positions to step forward. And so if this delta value is allowed to approach, like 5, 10, 15, anything higher than that, then that would introduce so much error into this attractor function that everything would just fly apart and it wouldn't be captured by the attractor function really that much anymore. At least it wouldn't stay within the bounds of, the visualization.